Welcome back. We'll back to lesson 5.3, segment relationships. Let's get started. The first theorem says, in the same circle or in congruent circles, two minor arcs, remember minor means less than 180 degrees. Two minor arcs are congruent if and only if their corresponding chords are congruent. So if you notice, this chord is 6 and this chord is 6. That means the arc that is formed around the chord is congruent to this arc that is formed around the chord, because since the chords are congruent, the arcs are congruent. So x would be 121 degrees. X would be 121 degrees. And we will do example B in class. So that theorem again says, in the same circle, or if we know that two circles are congruent, two minor arcs are congruent if and only if their corresponding chords are congruent. So, for example, up here, BA is congruent to CD. That means BA arc is congruent to CD arc. The next theorem states, in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant. Remember, it means equal distance from the centers. So if I know that FE is equal to GE, they're the same distance apart, that also means that the chord AB is congruent to the chord CD. Okay, if the two chords are the same distance away from the center, the chords are then congruent. So in example 2, I see that the chord ST is 18 units away from center W, and the chord VU is also 18 units away from the center of the circle. That means these two chords, ST and VU, are congruent to each other. So ST, 6x minus 5, is congruent to VU, which is 13, plus 4x. So if we can go ahead now and we can solve for x. Little equation. Subtract 4x from both sides, I have 2x. Add 5 to both sides, I have 18. Divide both sides by 2, x equals 9. Two-step equation right there, guys. X equals 9. Okay. So example B is done the same way. If you want to practice it on your own, go ahead, but we will do it in class. So as a recap, if two chords are the same distance away from the center of the circle, they are equal to each other. The chord product theorem states that if two chords intersect inside of a circle, then the product of the lengths of the segments of the chords are equal to each other. So as you can see, chord CD is intersecting chord AB. Okay? So when I break up those two chords, they're equal to each other. The product of the two segments are equal to each other. So AE, this piece, times BE, that piece, is equal to CE, this portion, times DE, that portion. And it may not look like that to scale, but you have to trust the rule. So we're going to find the length of each chord. So in order to do that, I am first going to find x. Well, I easily know what HJ is. There's HJ. If H to G is 9 and G to J is 8, HJ is 9 plus 8. HJ is 17. Okay? So now I'm going to need to find Ki. In order to find Ki, I have to know what Gi is, which is x. Well, remember, we know that the lengths of the two segments, so 9 times 8 is equal to 6 times x. 6 times x. 9 times 8 is 72. 6 times x is 6x. I'm going to divide both sides by 6. Divide both sides by 6. X equals 12. So x equals 12, and I need to go back in and plug it in to find the length of ki. So 6 plus 12 is 18. Ki is equal to 6 plus 12. Ki is equal to 18. Now you may be thinking, but Miss Locke, Hj is 17, Ki is 18. Those aren't congruent to each other. Remember, I didn't say the two chords were congruent to each other. I said the product of the two pieces of the chord are equal to each other. So you can check this. What is 9 times 8? 9 times 8 is 72. What is 6 times 12? 6 times 12 is also 72. These two products are equal to each other. That's the chord-chord product theorem. We will do example 4 in class together, unless you would like to try it. Next up, a secant is a line that intersects a circle in 2 points, aka it's a line that goes through the circle. And this is an example of a secant. See if I can get that a little bit better on the line. There we go. There's your secant. It's going through the circle. A tangent is a line in the plane of a circle that intersects the circle at exactly 1 point. And here's an example of a tangent. This line is intersecting exactly at point B and only at point B. So secant goes through the circle 2 times, tangent only touches the circle 1 time. We have 2 more theorems. The secant product theorem, meaning 2 secants. Secant, 2 secants. If 2 secants intersect in the exterior of a circle, then the product of the lengths of one secant segment and its external segment equals the product of the secants of the other secant segment and its external segment. Excuse me, and that's a lie. So first of all, it says if the secants intersect in the exterior. Well, this secant AB, E, is intersecting with CDE right here at point E. So yes, they are intersecting in the exterior of the circle. They are intersecting outside of the circle. So what this problem is saying is that AE, the whole secant, times BE, the outside part, is congruent to CE, the whole secant, times, oops, sorry about that, times DE. Okay, so the whole segment times its external piece is equal to the whole segment times its external piece. The secant tangent theorem says if a secant and tangent, so if a secant and a tangent intersect in the exterior of a circle, meaning outside of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. So it's almost the same thing. The whole secant with its external piece times its external piece is equal to the external piece but squared. And we would square it. Okay? So we're going to do a practice of those, but we're going to do the majority of these in class. So we're going to find x. So example 5a, we're going to find x. Well, I need the whole piece. So SP times RP is equal to UP times TP. The whole piece times the external piece is equal to the whole piece times the external piece. Well, SP is 14 because 8 plus 6 is 14. RP is 6. So I have 14 times 6 on my left side is equal to UP, which I don't know, it's 7 plus X. Oops. Sorry, not 7 times X, 7 plus X. Times TP, which is 7. 14 times 6 is 84. I'm going to distribute my 7 in. 7 times 7 is 49. 7 plus 7 times x is 7x. Subtract 84 from 49 from both sides. We have 35 equals 7x. So x equals 5. That's what the problem asked us to do, was to find x, and we did. We don't have to find the length of UT or the length of UP, just finding x. And we will do examples B and C together in class. Hope this helps, guys. If you have any questions, please make sure you write them in the margins of your notes, and I will see you next class. Have a great day.